Today we are going to discuss about Burrows-Wheeler algorithm. So what is Burrows-Wheeler algorithm? The Burrows-Wheeler algorithm was published in the year 1994 by Michael Burrows and David Wheeler in a research report, a block sorting lossless data compression algorithm. The algorithm consists of several stages and these stages are performed successively. The input and output of each stage are blocks of arbitrary size, but the size must be specified at the beginning of the whole compression process. With the decompression of the algorithm, the data which was compressed earlier by the algorithm can be returned to their original form. Remember that there are countless different versions of this algorithm. Outline structure of the Burrows-Wheeler algorithm. The process involves three steps. There's the input, which goes into BWT, that stands for Burrows-Wheeler transform, which then goes into MTF, which stands for move to front transform, which then goes into the last step, which is EC, which stands for entropy coding, and then you get your output. What is done in these stages? The first stage of the algorithm is the Burrows-Wheeler transform. The aim of the first stage is to sort the characters of the input so that the identical characters are close together, or better, form sequences of identical characters. The second stage of the algorithm is the move to front transform. In this stage, the characters of the input, which are still in the local context, get assigned to a global index value. Thereby, the characters which occur more frequently in the input get a lower index value as the less frequent characters. It must be mentioned at this point that the first two stages of the algorithm do not compress the data, but these stages transform the data with the result that they can be compressed better in the following third stage. The third stage of the algorithm is the entropy coding. In this stage, the real compression of the data takes place. Normally, the Huffman coding or the zero run length coding is used as entropy coder. Confusing, right? You can understand it better with an example coming up in a few moments. But before that, a few quick points to remember about Burrows-Wheeler algorithm. Burrows-Wheeler transform creates a representation of the data which has a smaller working set. The transform data is compressed with move to front compression. The decoder is quite different from the encoder. The algorithm requires processing the entire string at once. That means it is not online. The BWT has two main applications, compression and indexing. Burrows-Wheeler works in a block mode, where the input stream is read block by block and each block is encoded separately as one string. This is general purpose algorithm. It works well on images, sound, text, and can achieve very high compression ratios. Applications of Burrows-Wheeler algorithm. Traditionally, the major application of Burrows-Wheeler transform has been the data compression and efficient storage. However, recent research on the Burrows-Wheeler transform has shown the versatility of the BWT, and hence efforts are shifting from its traditional application in data compression to other areas of study. BWT also provides an effective mechanism for rapid pattern matching. It has many uses, focusing on new and emerging applications. Some of the applications also relate to new data compression applications. Given that the original purpose of the Burrows-Wheeler transform was for data compression, it is no surprise that the method could be used for compression of other types of data. BWT can be used for the compression of specialized data sets, including compression of test patterns used in automatic testing in chip manufacturing, image compression, and compression of biological sequences. And now onto the example.
Today we will talk about Burrows-Wheeler transformation. As you already know, Burrows-Wheeler transformation is used to compress string. Our friend Dev has already discussed about Burrows-Wheeler transformation given its introduction. So we'll take an example and solve it and prove how to do Burrows-Wheeler transformation. The string we used in this tutorial is banana with a dollar sign. The dollar sign indicates the end of the string. Now we have to do is rotation of the string. First we'll write the dollar sign which is at the end of the string to start the rotation. Then we'll take the second last character, that is A, and put it in the first place to start the second rotation. Then we'll move to N and then so on till we get the original string back after rotation. Then we'll finish all our rotation. Now we do is based on the first column, we'll sort the rows. We'll sort the string alphabetically and get the result. Now this is the final sorted step. Now we save the last column and the last character of the string. Wheeler's transformation. We only save the last column and last character of the string. In this case it is dollar sign. Based on string we get the original string, that is banana, back. The advantage of Burrows-Wheeler transformation is that the repeated characters are nearby and when we apply the compressing algorithm it is more efficient. The string we got after the transformation is A, N, N, B, dollar, A, A. Now we'll try to get the original string back from the compressed string. We know the position of the last character, that is dollar sign. From the dollar sign we'll start getting the original string back. Since we know the position of the last character, that is dollar, we move vertically and get our first character B in the first column. Since this is the first B, we'll get to the last column of B and fetch A vertically. This gives B and A. This is the third A, so we'll go to the third A in the last column, and from the last column we'll go vertically and fetch N. This gives BAN. Since this is the second N, we go to the second N in the last column and fetch A vertically, and this gives BANA. From the N, we will get to the first column of A and we will get BANA. From BANA, after that we will get N and so on till the procedure is complete. We will get the full string BANA. Now what about the dollar sign? The dollar sign indicates the end of the file. We'll get to the dollar sign. Dollar sign is at the starting. At the last we get the dollar sign from A. Since the dollar sign indicates the end of the string, we'll fetch the dollar sign and our string is complete. That's BANA with a dollar sign. And this denotes the end of string. Thank you. Let's talk more about Burrows-Wheeler transformation. To understand why this creates more easily compressible data, consider transforming a long English text frequently containing the word the. Sorting the rotation of this text in group rotation, starting with he together and the last character of the rotation, which is also the character before the he, will usually be t, so the result of the transform would contain a number of t characters, along with the perhaps less common exception, such as if it contains Brahme mixed in, so it can be seen that the success of the transform depends upon one value having a high probability of occurring before the sequence. So this in general, it needs fairly long samples, a few kilobytes at least, of appropriate data such as texts. The remarkable things about the Burrows-Wheeler transformation is not that it generates a more easily encoded output. An ordinary sort would do that, but this is reversible, allowing that the original document to be regenerated and the last column data. The inverse can be understood this way. Take the final table in the WT algorithm and erase all the last columns. Given only this information, you can easily reconstruct the final column. The last column tells you all the characters in the text, so just sort these characters alphabetically to get the first column. Then the first and last column of each row together give you all pair of successive characters in the document, where each pair are taken cyclically, so that the last and first character form a pair. Sorting the list of pair given the first and second column containing in the manner, you can also reconstruct the entire list. Then the row with the end of the file character at the end is the original text, reversing the above given sample like it's done like this.